grab the screen.
Yep. So our next talk is by David Frayer. He's a scientist here at the Green Bank Observatory, and he is going to give us a large overview on what the GBT is, the kind of science that we observe, and how we go about doing that. So take it away, Dave.
Okay, thank you. You can hear me, right, Will? And you can see my slide? Okay.
Yep.
Well, good morning, everybody, and thank you, Will. We're going to be going through some of the GBT capabilities in this hour. I can't, while I'm presenting, I actually can't see the chat session and stuff. So put the questions in the chat. I'm not sure if we have things wide open where you can actually unmute and talk or not. Will, do you know if that's the case? If they can interrupt? I don't mind people interrupting if there is a specific question, or do you want to wait and just do it by the chat?
If you don't mind the interruptions, we don't have all that many people that it would be impossible to do. So anyone can interrupt if you're fine with that.
Yeah, I'm fine with that. We're not, our schedule's pretty loose when we do these in person. They're very informal. They tend to seem more formal when you have to do it virtually. You can't see people face to face. Okay, the outline of what I would like to go over. Karen's already given you a little bit of overview of the GBT. I'll do a little bit more. And I'm even going to add a little bit of just radio astronomy, because I realized in previous sessions that different people are coming into these training workshops with different background. We won't get too in depth there, but just some basics. Then I'm just going to do a show and tell of some of the GBT science areas, just to see the types of things that scientists around the world use the GBT for. Then we'll get in more into the nuts and bolts, the capabilities and performance of the GBT. And then we'll get into some practical aspects, such as observing strategies based on what you're trying to do, because you're observing tonight. You'll be broken up into teams this afternoon, and you have to figure out what you want to do tonight. The overview is the biggest movable telescope in the world. Karen already mentioned it covers all the way from 100 megahertz all the way up to 116 gigahertz. It makes it very powerful. From my point of view, there are four main key characteristics of the GBT that makes it unique. It's big. It's a big light bucket. The 100-meter class telescope gives you high sensitivity and high spatial resolution for a single dish telescope. As Will mentioned, it's located in a radio quiet zone. We both have national protections as well as additional legal protections from West Virginia. The idea here is to minimize the RFI that the telescope sees. Its off-axis unblocked design makes it very powerful for studying faint extended emission, makes it unique. And the active surface, we can deform the surface as it sags due to gravity, and that allows us to be able to push up into the 3 millimeter observing window. So the radio quiet zone is very big. Most people don't know. There's lots of people who live in it and they don't know they live in it. But it doesn't mean you don't have cell phones anywhere in this area. It just means we restrict the ability to put up transmitters such that it will interfere with the telescope. I have a cell phone. I'm just over the mountains from Green Bank, but they don't put the cell phone tower on the top of the mountain. They put it down the mountainside, so the cell phone emission doesn't go up over the mountain and gets to the telescope valley, but stays in our valley over here, for example. So it's not RFI free, but it's about as best as you can do, certainly in the continental US. The unblocked aperture, Karen already showed this, but it just shows the relative ability to take images with an unblocked aperture. These two images were based on the same expected sensitivity, and you can see the image to the left here. It's from Bonn. It's a great telescope, but they have blocked aperture. You basically, side lobes radiation hits those feed arm supports, and it's hard to go very deep and see extended structure as you can do with the GBT. So that the advantage here is just due to the clean beam of the GBT. The actuators, here's a picture of the edge of the dish. Those little things here. So we have an actuator on each corner of each panel. I have a couple thousand panels, a couple thousand actuators roughly, and those actuators can move. and we can get the overall RMS of about 230 microns across 100-meter dishes, which is quite fantastic. And that basically enables us to observe at 3 millimeters. Without that, we wouldn't at 3 millimeters. In terms of the optics, if you looked at it this way, I mean, the main reflector, we can have a sub-reflector up here. This is showing prime focus, where we have this is prime focus feed that comes out. Will, can you see my cursor when I'm moving it on the screen or not?
Yes, we can.
Yeah.
Good, okay, because I just wanted to make sure. I never, but then this can get pulled away and the light can hit the secondary and then come down into this thing here, which is the receiver room. And here's the sub-reflector. And then, so in Gregorian focus, we have our higher frequency receivers, L band, 1 gigahertz up to 115 gigahertz. Under 1 gigahertz, we have a prime focus feed, and that's this thing here, it swings out. So the light hits the main dishes down below, hits here, and then goes into one of the horns here. And on scale, our sub-reflectors are pretty big. It's an 8 meter secondary, so it's like pretty good size. This is on the top of the receiver room. If you were able to take a tour when we do these training workshops, we normally get people up on top and you can look out, beautiful valley. There's 140 foot down below. It's a big telescope in itself. It looks pretty small when you're on top of the GBT, because the GBT, of course, is huge. So this is the top of the receiver room. This turret rotates around. That's S band right now in the focus position. There's L band. So anyway, that's how we change the frequencies. You rotate that turret around. Underneath, if you're in the receiver room, this is what it'll look like in the receiver room. And the feeds come down. That's where electronics are. As well, it always moves. I got this from Ron, but anyway, it's just a picture. It moves in elevation like this. And then we have it on the, well, we call them trucks, and go along big wheels and 4 trucks, in which it supports the weight of the telescope, 17 million pounds. Okay, basic radio astronomy. We use units of Jansky. So he was he's sort of one of the founders of radio astronomy, and it's a very small unit of power, or flux density, I should say. And it's 10 to the minus 26 watts per meter squared per hertz. So 10 to the minus 26 is very small. So you think about your light bulbs that are 100 watts. So here we're talking 10 to the minus 26 of a watt. We also, a lot of times, and I fall into this more and more as I get older, using engineering units, decibels, dBs. We talk in dB units. Think of it like sort of like magnitudes, but without the minus sign. But anyway, so if you're talking about 30 dBs, that's a factor of 1,000. Just so to understand what we're talking about.
Hey Dave, you have a question in the chat.
Yeah.
Asked, what is meant by 6 degrees of freedom of the subreflector?
Oh, well, a lot of subreflectors just have one axis, and you can rotate it really fast. But here we have a full. There's six axes, so you can. But yeah, so yeah, it can move. It's I forget the name of the platform, but you have multiple actuators working together. We have multiple X. We have, I guess they should maybe have, it has 6 actuators is what it actually means. Because you have multiple we have X, Y, Z coordinate systems, and there's multiple actuators on each of those axes, basically. So you can tilt and move it and translate that. Subreflector a lot more powerful than what a lot of actuators are. Because we use a subreflector, since the telescope sags, it's really heavy and big, and then it's on the feed on, we change the actual parabola that we look at as the elevation sags. So the subreflector, as you change in elevation, it's always moving a little bit to keep everything in its focus. So I guess maybe we shouldn't say 6 degrees. It's working in 3D space, but there's 6 actuators. So that's what they mean, 6 mechanical degrees of movement. That was a good question. I might update my slide for that. Thank you. So we're just doing the basic radio astronomy. I just want to mention some of the types of observations people do. You can do broadband continuum observations. We don't do a lot of that here with the GBTs. Single dishes aren't necessarily the best instruments for measuring continuum emission, but you can measure. We use continuum at 3 millimeters. With the Mustang is the continuum. You can measure what we call synchrotron emission. You basically think of electrons and ions spinning around magnetic fields. We have what with free emission, we can call that thermal emission. You can get that from H2 regions, and it has an SED that looks like the green line. The synchrotron emission is bright at low frequency and they die away at high frequency. Supernova remnants and AGN are really bright in the synchrotron emission. I should say, like in comparison, like if you do optical astronomy, you go out and look at the night sky, you see nearby stars. If you had eyes that worked in radio wavelengths, what you would see is distant AGN, and that's the point sources in the sky, and radio sources there tend to be AGN at sort of low redshift. You can do spectral line work, and that's typically a lot of times what we do in these workshops. People do chemistry, different molecules to study some chemistry. Neutral hydrogen everywhere. And it's very easy to observe because it's at low frequency and you can observe it even if it's raining, and we might get rain here this afternoon. I haven't looked at the weather tonight. We also can do carbon monoxide on the telescope, but we won't be doing it for this workshop. Argus is right now currently warmed up, and the weather, at least tonight, is going to be anything suitable for 3 millimeter observations. But the spectral lines are just narrow features that you can have rotating molecules. Hydrogen is due to a spin flip of the electron. Pulsar work, a lot of people study pulsars. The rotating neutron stars, you can think of use the analogy of a lighthouse spinning around and the radiation. Some of them can spin very, very fast. And every time you get a little blip, and this is sort of shows as a function of time. Here, when you're doing pulsar work, you're doing time domain astronomy. And with the fast radio bursts that are being discovered, it's more and more research is into transient radio sources in the sky. Okay, I'm not going to get in. I had more slides here, but I took it out because I wasn't going to get into all the math on that here. But anyway, just the antenna beam, what you have is you have a big main lobe beam. And when you look at something on the sky, that beam is convolved with your source brightness, and that's what you see. Well, the power of the GBT is these side lobes here in dB. Instead of being at minus 10 dB, which is 1% like a typical traditional radio telescopes, we're down at minus 30 dB. So the side lobes are way down at a much lower level on the GBT. Terminology like antenna temperature, system temperature. Like the system temperature, just think of all the power that the antenna sees. That from the source, that from the receiver, that from the atmosphere. Also, you see a little bit from the ground, the cosmic microwave background, all the power that comes in. We call it, that you measure a system temperature. And then your ability to detect something on the sky is proportional to your system temperature, your noise that you would get, proportional to your system temperature. And like when you're doing spectral line work, the longer you integrate, or if you smooth your data over more frequency, you can beat down the noise basically. And this is what, if you ever hear anybody use the radiometer equation to estimate your sensitivity. We have a sensitivity calculator that does this for you, but that's sort of the background behind it in terms of just terminology. Okay. I don't really think about it that much, but I find this sort of interesting anyway, is typically in astronomy, almost all fields all the fields in astronomy actually treat the light as photons, basically. Electromagnetic radiation, you can treat it if you had your basic physics as a wave and as particles. The other fields of astronomy treat light as particles, photons. Radio astronomy takes advantage of the wave properties of electromagnetic radiation. The electromagnetic waves come in, we actually mix it with another frequency, And this is radio terminology, and that's why it's sometimes useful over it, because it's some jargon if haven't done radio astronomy. So they're called heterodyne methods, and you're basically mixing in a radio signal at another frequency with your sky frequency to produce a new frequency. We call that the IF, or the intermediate frequency. We'll just say the IF. So when people are talking about the LOs, the local oscillator, the IFs, the intermediate frequency. And the reason we do this is you can basically you can see all the frequencies across the entire sky. Well, we go from 100 megahertz up to 116 gigahertz, but all that goes through and comes out the same back end of the telescope. Excuse me, I'll explain that. The same electronics. Otherwise, you would have, if you didn't mix it down to some common frequency, you'd have this way you just have one IF system, and then you have the LO mixer can introduce different frequencies and such that you can mix everything down to the same common frequency. So the stages in terms of radio astronomy, you have the antenna, which gathers your radiation, and then you convert that electromagnetic radiation from free space into an electric form via the feed horn. Then you amplify that electrical signal with a low noise amplifier, and we say LNA, more jargon. We mix it with the LO to convert it to a different frequency. It's a lower frequency typically when you're observing a higher frequency, and that enables us to transmit over the IF back to what we call the back end, which is the spectrometer. So in terms of the terminology, the front end is the receiver, and the cold part's there, and you usually have the warm electronics, and then you have an IF system. And for the GBT telescope, we were doing the tour. All this stuff here is in the receiver cabin, but then we have a couple kilometers of optical fiber to go into the control room, the Jansky lab, where we have the back end. So all the computers and back end that does the actual detection they're not at the telescope. They're in the Jansky lab and the back end. So we have the front end, which is the receiver, the back end's the spectrometer. Okay, just really basic radio astronomy. Now I'm going to jump to basically talking about some areas of GBT science. We do a lot of pulsar work. I would say at least 30% of our time is probably spent on pulsars. Maybe another 30% of our time is spent on neutral hydrogen, looking at nearby galaxies or even within our own galaxy. And then the other roughly 30% of time is done for higher frequency work. We do a lot of, this is an up and growing field, chemistry, astrochemistry, studying organic molecules. We do a little bit of high redshift CO. I do some of that. We do maser work. A lot of star formation is a big thing in terms of high frequency ammonia mapping in nearby star forming galaxies. And now we're pushing those, studying nearby star forming galaxies using the 3 millimeter and 4 millimeter transitions of dense gas tracers. And then we, as Karen mentioned, we're starting to get into planetary radar, and we also have breakthrough lists in the SETI project that uses 20% of our telescope time. In terms of a breadth of science, this is just to try to show that, yeah, we cover a lot of fields of categories down along the x-axis. We're just picked from the Astro 2020 decadal survey sort of categories. And this is just trying to do a bookkeeping to show the number of papers in each of these different fields. Galaxy evolution, we do a lot of stuff, star formation. In terms of stars and stellar evolutions, the stars themselves are not very bright in radio wavelengths. There's not a lot in comparison that we do. So you don't see much in resolved stellar populations, but we do ISM star formation. And this is just to show that there's a significant interest in the community in different areas of using the GBT. So the GBT is a telescope or a single experiment. It's a general observatory, and people use it for all kinds of things. This is a listing I took from our webpage. It's just a screenshot as listed. Well, I've put the date on it to remind me if I use this slide in the future, but this is what we have now. These are the surveys that are undergoing the larger surveys. So the Green Bank Ammonia Survey studying, and then we have some galactic hydrogen surveys. This is an extragalactic H1 survey, pulsar surveys, ionized gas survey. Then we have a dense molecular gas survey of nearby galaxies. Then we have some chemistry survey, Gotham, which build upon Primos, which is not on here anymore. It's completed survey, the nanograph survey, related project. This is Pulsar project, and then a higher frequency project, just to show some of the larger surveys. In terms of pictures, here I'm going to go through these pretty quickly just to show and tell. We're getting radar. This is not an image from the GBT. It's just showing there's lots of things flying around near the Earth, and it'd be nice sometimes to take pictures of them. You can track them, and and having radar information about it, you can learn more about their orbits, if they're rotating and such. This is an example of something that came by. I can't actually see the date on here. In 2015. So Goldstone transmitted, and then we received. So that's we're doing more and more of that. Whoops. The pulsar aspect of it, people argue, and I'm not going to disagree, that the GBT remains the world's premier pulsar observatory. Unfortunately, Arecibo had collapsed. They have some sensitivity, but the GBT can see the wide range at 85% of the total sky. So there's a lot of pulsars. The big driver force is a nanograph in terms of trying to detect cosmological gravity waves, basically. And they've been working on that for several years, and they're getting closer and closer. And they're borderline, potentially in the next 5 years, they'll make a detection of gravity waves if the current data holds up. Massive pulsars. I mean, when I went through graduate school, pulsars weren't supposed to be, or neutron stars weren't supposed to be, 2 solar masses. But so this constrains the equation a state of like very dense matter, for example. H1, the unblocked aperture, you can take advantage. If you zoomed in here, there's too much on this slide. This is what you'd see optically, this little galaxy here, but you see there's H1 everywhere. You just don't see it. And optically, you have to go deep. You can, and around bright nearby galaxies, you can study these H1 clouds that are falling in. You have the Magellanic Stream, which probably people might be familiar with. You can see remnants of a stream of gas stripped out of, a neighboring galaxies, well, the LMC and SMC. The H1 survey, MANGA, 2,000 low Z galaxies. If you do some H1 work, H1's always good to do. So if you look at an edge-on galaxy, you can see it like these double horn profiles, because you get the part of the disk going away from you and coming towards you. If you look at something face on, it will look narrower and tend to be Gaussian, because you're just seeing the velocity dispersion through the disk. But anyway, chemistry. I think this is one of our biggest expanding fields, and well, I shouldn't say that. I'm biased. I think it's sort of interesting. People are interesting to study the chemistry. Is always curious. Trying to find basically organic molecules and trying to understand the life cycle of chemistry and the pre-organic molecules that we're seeing in space. I mean, if you go back many years, nobody thought you could have organic molecules in the molecular, out in interstellar media, but we're seeing that. And this slide's somewhat out of date, but there have been 20 plus molecules found on the GBT, and this work is ongoing at a pretty fast rate. It's pretty exciting. Star forming regions, this is one of my favorite GBT images by Rachel Friesen, and this shows the GBT ammonia image of the Orion molecular cloud in the red, basically, with the infrared or near infrared WISE image in the background showing the dust image. This is from the gas survey, the GBT ammonia survey of nearby star forming regions. Disco gas, this is a new project starting up to measure the dense cores and star forming regions using a dense gas tracer, the N2H+, which is up at 93 gigahertz. They're going to look at the nearby Perseus star region, which is like 100 cores. So you're trying to understand the connection or the kinematics within these cores and how star formation forms. The GBT is used with other antennas around the world for VLBI, very long baseline array interferometry. I mean, this is a project that 2 years old, but it's quite spectacular in terms of being able to use stellar pair, just basically doing parallax. Stars aren't very bright in radio wavelengths, but if you're sensitive enough, you can see some stars, and they actually measure direct parallax distance to the Pleiades, which is a standard candle, which helps understand this, the extragalactic distant ladder. A lot of masers have been discovered on the GBT, and the maser work, the water maser work, that's as is ammonia. You can measure the masses of black holes, and you can actually get, by studying the kinematics, you can actually make an estimate, since you can figure out how far away the objects are, make an estimate of the Hubble constant, independent of all the cosmological modeling interparameters, which is a nice measurement to have. Just a pretty image of the M87 jet at 3 millimeter wavelengths. This is the source that shows up as a donut, where the Horizons telescope at 1 millimeter, where they have those beautiful images of the surrounding area of the black hole. High redshift CO, mentioned that, and here's a picture in continuum from Alma. But what we use GBT for, we observed in CO to get their redshifts. So they're found virtual, you can observe them from Alma, but if you're trying to figure out how far away the objects were, this is a lensed object, so the background, there's a foreground object that's lensing it, and this is what it looks, you see the dust emission in the background. So this is a high redshift object, redshift of 3 basically. But to get the redshifts, we observe with the GBT, and we can see the CO lines, and knowing their actual redshift, you can just search for sources. In this particular spectrum, we are doing the on and off. We looked at 2 sources, and we got the reference source as well as the other source. So we got 2 redshifts for one set of observations. Excuse me. The Mustang does 3 millimeter observations in continuum. They've been using that instrument last week and regions and other things as well, but a lot of their group is studying distant clusters, and you can study the kinematics and the structures and the subclusters. Clusters aren't very simple. I mean, we used to treat them as spherical objects with hot gas, but there's a lot of interesting stuff going on. You have subclusters merging, and there's shocks and all kinds of complex physics going on in clusters, which Mustang is helping to uncover. Okay, now that's sort of the show and tell on some of the science, the breadth of the science. Now I'm gonna get more into the nuts and bolts with the GBT capabilities and its performance. Here's our receivers on the GBT. Excuse me. This list and shows we have different receivers covering all these different receiver frequency bands. We use these bands, and what's available for us in the coming days are these here: L band, S band, C band, X band, and the KFPA. Argus is warm, and K band, KA, and W are not on the telescope, and they're having problems with one of the controls, prime focus. So we're probably not going to use the prime focus either. So when you set up your projects this afternoon, these are the receivers that you can use. So L band, you can do H1, KFPA, you can do ammonia observations, and I haven't looked at the breakdown. The Pulsar people, instead of using prime focus, are going to have to focus on the L band receiver, basically. I guess you could do S band too, but it'll probably do L band, my guess. Okay, the back ends, we have the Vegas spectral line back end, and we also use Vegas and Pulsar modes to do the Pulsar science. So I would suspect that most of us, that's what we're going to primarily be doing. We could do some continuum work. They are. CCB, you can only with the Ka band receiver. We won't do that. We're not going to be doing any VOB work, and we're not going to do radar work. So most likely what we'll use is Vegas or the DCR. You show the system temperatures across the band for the different receiver bands. It goes up a high frequency. This is due to the atmosphere. And this is with the galactic background at very low frequency, but we'll be down here. We'll be observing an L band. So we can do anything from L band up to the KFPA. Now, at low frequency, we don't have to worry about the atmosphere that much, but above 10 gigahertz, you really do. I mean, and we're going to see it even more today. So your system temperature here is a combination of all this stuff. And if you in a higher frequency atmosphere starts to really dominate your noise of the telescope. But most people in the US anyway, you don't think of a dry site out, east of the Mississippi, very many dry observatory sites. And it's true in the summertime, we're not really dry at all. But in the wintertime, we're not at super high elevation. We're only up at about 2,700 feet. We actually do get pretty good dry weather. About 50% of the time during the winter season, you have an acceptable level of water vapor, low enough water vapor, 10 millimeters of water vapor or less to observe, which is sort of surprising because that's sort of the winds. It's a big telescope, so it can jerk around in the wind. So we have wind limits too at higher frequency. You really want the be under 5 miles per hour if you're up at 100 gigahertz. At low frequency, it really doesn't matter. You could observe without affecting the quality of data at almost 70 miles per hour. You'd observe through the winds. We don't do that because we don't want the telescope to get ripped apart. So at above 35 miles per hour, we stow the telescope in a way to have the wind go under the dish basically and not treat the dish as a big sail. You wouldn't want to do pulsar observations at like 10 degrees on the horizon into the, whatever, a 50 mile per hour wind. That wouldn't be good. Now, how do we schedule? We'll hear later in the workshop how we do scheduling. We have this dynamic scheduling system, and it is truly dynamic. Tony runs it every day in the morning, and a new schedule comes out. And typically you can have 24 hours to 48 hours advance notice of your observations being scheduled. So when you have a project, it's very important. You fill in your blackout dates, you stay on top of it. You get emails. You might want to set up text messaging to yourself, but just saying you've been scheduled, because occasionally you'll even get less than 24 hours notice. And how the system works is basically when the weather's predicted to be good, we observe at high frequency, and when the weather is bad, we observe at low frequency. And this enables us to leverage all the high frequency weather that we get here instead of having a fixed schedule. Because if you had a fixed schedule, you'd be spending a lot of time doing low frequency, and the high frequency work would never get done. So without this kind of a system, you really couldn't do high frequency work here. In terms of the surface and our ability to observe at higher frequency, you have to really work hard on the telescope and get the telescope as good as it can be. There was a big improvement in 2009 to improve the surface. And the top just shows a progression of that work in 2009 with fixing the actuators and making measurements, and down below shows the effect of the tightness of the beam. So if you have a noisy surface, you have a big beam and you can't see a high frequency, and clean up the surface, you have higher efficiencies and your beam's a lot tighter. And this shows a history of the surface improvement from excuse me, all the trees have come out in full bloom, and we have all that maple tree yellow pollen floating around, and that's starting to hit me. But anyway, telescope was built in 2000. This curve here shows the effective aperture efficiency at 80 gigahertz, and over time, we've improved that. So in 2009A, I'm not going to go into all the details here. This is documented. There's a memo. Here's the work on the actuator from A to B. You see, there's vast improvement. That's when we made the telescope. Before 2009, you really couldn't use a telescope at high frequency. But after that, then we've improved it, and you can basically. And this is basically ever since about 2010, the curve was similar to this. So we've been pretty flat in terms of our aperture efficiency, approaching like almost 40% at 80 gigahertz. We can observe up to 116 gigahertz. It's just on a log scale. Orion's really bright, but anyway, this was a second spectrum taken with the new Argus instrument back in 2016. I guess it's not new anymore. That's 5 years ago. Cameron already showed this. One of the observations showed that we could reach our theoretical beam. With Argus, the GBT does achieve good beam sizes, typically about 1.2 times lambda D. Depending on the conditions, it can range from about 1.15 to it can be even up to 1.3 lambda D. And when the weather isn't that great. So when the surface isn't very good, your beam is bigger. When the surface is better, the beam is tighter. It just shows that we can calibrate the telescope, and there's a lot of technical stuff here. If you're interested in the GBT's performance, the details, you can look at that GBT memo 302, the table of all the parameters. And basically, if you look at it in terms of, point source, aperture efficiency, main beam efficiency, you can measure the near beam air pattern. So if you look at in terms of the power and the forward direction on the sky, most of the light we see is almost 99%. That means only like 1 to 1.5% sees the ground, which is really good. And you get that because we have an unblocked aperture. And you multiply that by the forward spillover efficiency B, you multiply those two numbers together, it's 95%. That basically gives a fractional power from the antenna within about 1 degree on the sky. So typically you don't have that with radio telescopes. They're not nearly this thin. This is because of the unblocked aperture. So if you point to a point on the sky, roughly about 95% of that, the antenna power is within 1 degree of where you point, which is quite spectacular. That's at higher frequency. The beam is bigger. It expands a bit. Okay, in terms of the performance of the telescope itself, in terms of pointing, so we have a pointing model. If you go out and you start up a project and you just randomly point somewhere on the sky, there's some variations, but roughly the average pointing error is blind pointing is 10 arcsecond error. Let's say you point on one point in the sky and then you slew around, 3 hours later and point somewhere else. On average, you'd be about 5 arcseconds off. That's our all sky offset pointing error. Now, if you point near an object and you offset a little bit, let's like 10 degrees, and that's what we do at high frequency, the underlying pointing errors are of order 1 arcsecond, and we can track that telescope, the big telescope, to about a half arcsecond, maybe a little bit better. We need to update the measurements. We improved the servo system a few years ago, and it's hard to make these measurements. We need to make more accurate measurements. It's easy to make measurements when you're not tracking very well. You can see large effects, but once you improve things so much, it's harder and harder to make these smaller measurements to confirm the performance. But anyway, we think the tracking error is about 0.5 arcseconds or less. The surface, so what that means on these numbers here, if you're observing at L-band with a 9 arc minute beam, you don't care about any of the pointing errors. But if you're observing at 100 gigahertz with a 7 arcsecond beam, then you have to worry about these offset pointing errors, and you want to be able to, you want to point more often to maintain it. Maintain your pointing accuracy. The surface accuracy, without the active surface turned on, where you're adjusting the actuators, and the surface error is like 0.5 millimeter. And then we've improved that down with all the active surface, and then we have out of focus holography correction that we call them OOF, these OOF corrections during the day and during the night. At night, we get better performance, hard to get good performance during the day. And that's why we're hoping to leverage LASI in the future. But we can push it down to about 230 microns or 0.23 millimeters. The long-term goal is to hit 200 microns or 0.2 millimeters. That's about what we can do. I mean, the panels itself, the subreflector and everything else, we won't be able to get really down below that, but that's sort of our floor baseline. If we could model everything perfectly, that's what we could get down to, about 0.2 millimeters. Observing strategies. Okay, now I'm going to go into switch gears a little bit to talk about the actual specific types of modes of observations and how those mesh with your science goals. So obviously your observing strategy depends on what you're trying to do. And the GBT provides a lot of different observing options, multiple instruments and several observing modes. You could observe in thousands of different ways on the GBT. This makes it extremely powerful, but it's also more challenging in terms of doing the software reduction on the data reduction size. If you observe, for example, Alma or the VLA, you can only observe in a few different ways. And that way you can write pipeline software to handle those use cases. The GBT, we let users, we will open it up. We let them turn and all the different knobs basically. And we have a lot of knobs, but the basic sort of, I mean, this is pretty simple stuff here in terms of like the decisions you need to make. The receiver, of course, you pick your receiver based on the frequency that you're observing, because some receivers only cover specific frequency ranges. And the back end that you pick are typically done based on observing time. You know, what you do on your back end, that's how you set, you do line observations or continuum observations or pulsar observations. You can configure your back end differently. And then your observing technique are based on your science goals. Are you doing a point source science? You're trying to map a large field? Are you looking at narrow lines or broad lines? These are types of considerations that go into trying to make decisions on how you take your observations. And then the calibration strategies also depend on, you know, the receiver that you're using as well as your science needs. So what does a radio telescope measure? Well, I should update this slide. This is pretty low tech here. But anyway, the antenna temperature, TA, is measuring everything. Like it's your source plus everything else, your receiver noise, your atmospheric noise. So what we do is we basically do on minus off. So when you're on the source, you see the source and everything else. And then you go off the source, then you don't have the source, and then you're basically in principle just measuring everything else. If you subtract those two, then you get your source, the signal from your source. And the techniques in radio astronomy are like the different modes of observing is really dependent. I mean, it's defined by how you carry your on minus off observations. There's lots of different ways to doing this. And the two main ways, we do frequency switching and position switching. And I'll explain this a little bit in the following slides. But the idea behind frequency switching is you're just looking at your source on the sky. You don't move the antenna. You flip the LO and frequency. And that's how you do your on and minus off. Position switching is more intuitive for most people as you actually move the antenna. You look at your source on the sky and then you move a little bit off, you get an off, and you can do an on minus off. Now we have at higher frequency, have a lot of, we have multiple beam receivers such that you can have, if you have two beams, you can do what we call dual beam position switching. So you don't spend half your time with your off and half the time with the on. You could put your target with the nod observation. And these bold letters mean that's the actual command you use to command the telescope, an asteroid command. So the nod command, for example, you can nod and put the source in beam 1, and then you put the source in beam 2. So you always have the source in one of the beams basically, and you do that by moving the telescope with nod. You can't move the telescope super quick. So we have this other mode called sub-beam nod, which actually moves the subreflector. You can move the subreflector quicker The subreflector can move nod about every 4.5 seconds. This is the maximum nodding speed, but it's roughly about every 5 seconds. That idea is you move the subreflector to move the source from one beam to the other beam. In terms of just showing some example data, this is a spectrum of some nearby galaxy in H1. This is the on spectrum. It's really bright. Normally, most of the stuff you look at is not this bright, but here's the pass band. That's the instrumental effect. The galaxy is this blob here. And then you have galactic H1 is this line here, which shows up in the off. So if you do the on minus off and do the reduction, you see the galaxy right here, basically, and you see how flat it gets. There's a little bit of RFI over here. Yeah, you can see it over here. And this here is the galactic H1. So this is the galaxy of interest that they were looking at. It just shows an on minus off example. And frequency switching, this is a schematic to show if you had a line on the sky like here, and you have your LO, this is your LO symbol for you're mixing in a different frequency, you shift your line. So at one LO frequency, the line doesn't show up in the middle of the band, it shows up over here, and then you put another LO frequency and it flips the line over here. And you see the underlying baseline is the same. So you can subtract these two from each other and you get a spectrum like, ideally you get, up and down. And then what we do is, and you do both of them, we call it folding it basically. So you do the subtraction and then you shift these and line those up. And then you average those together. So you see the bright signal here of interest. You see these effective, the subtraction pairs basically at half power because you're basically averaging those two. So this average with 0 is, cuts it in half. So that's what frequencies, in-band frequency switching spectrum will look like. Mapping, we can do different types of maps. We have a lot of people think of like on the fly mapping, for example. You're always moving the telescope. You're basically slewing the telescope back and forth. You're sort of painting in your image. So you go, actually it starts on this side, but anyway, we go here and back, you go back and forth. And that's those two modes, we call those RA long map and DEC flat map. But so we use that to map large areas on the sky, and you're typically not mapping very deep. Now, if you're doing a small area of the sky and you want to go really, really deep, it's more efficient just to do what we call a point map, where you just sit on, you take a spectrum, you move the telescope, take a spectrum, move the telescope. So you just sit, move, sit, move, sit, move. Yeah, if you're doing a smaller map, you might consider doing that. We have daisy mapping. Instead of just making rectangular maps, here you just slew across the source and then in these little petals. And you can do this pretty quickly, so the telescope doesn't have to completely stop. You're mapping back and forth like this, it stops. You have this 17 million pounds, you have to stop it, turn it around and start moving it back the other way. So these daisy maps, the idea is try to minimize the acceleration of the telescope and turnaround, and you make these little petals. And the advantage of this mode, we use this for point source continuum observations. When you're dominated, for continuum observations, you're dominated by what we call a 1/f noise, and which is just the instrument noise, and you need to slew fast over the source basically. And that drives your sensitivity more than your integration time or your bandwidth. It's how many passes over your source can you make. And a daisy map is an efficient way to maximize the number of passes you can make over a source. But the downside of this is the sensitivity is good in the middle of the map, but then you lose it on the outer parts of the map because you don't have as much coverage. So how do you pick your observing mode? Okay, the first basic question is, do you want to do frequency-based switching or position switching? If you have a narrow line and it's a non-crowded spectrum, we recommend frequency switching. But if you have a narrow line that's in a crowded spectrum, let's say you're doing chemistry, and you're going deep, and you have all these different spectral features and you're not sure what's what, you really want to switch your lines on top of each other it can be quite confusing to understand what you're looking at. It's okay if you just have like one or two, like a main line. If you have like a chemistry project where you're looking at a lot of lines, that might be challenging. You do frequency switching. And also if you're in a region that has a lot of RFI, you don't want to switch RFI on top of your line. So you have to be careful with that. In these cases, you might want to do position switching even with a narrow line. If you have a broad line, we recommend position switching. So what's narrow and what's broad? These are not hard and fast rules. You could actually do frequency switching with broad lines. I've done that before, and it actually works okay. But these are the standard traditional recommendations. A narrow line is, of order 10 kilometers or less. So you're talking about galactic science. Where broad lines, you're talking extragalactic science. 100 kilometers per second. That's a crude breakup between narrow and broad, and frequency switching and position switching. Okay, what mode do you use? Okay, then it's a question, is small source or large source? Large sources, you tend to want to do mapping. On small sources, smaller than your beam, then there's different options you can use. If you're at high frequency and have two beams, you can do the nod, as I was mentioning before, where you can move the antenna and put the source in beam 1 and then in beam 2. So you're always on a source. Subbeam nod, you do the same thing, but you do it with the subreflectors. We use subbeam nod. This is just for our telescope for Ka band, Q band, and Argus. That works well. If you're trying to do it, use subbeam nod for K band or W band, it doesn't really work very well. The baselines actually are not improved by that because those beams are too far apart, basically. So subbeam nod works when the two beams are close together at higher frequency. So we do that for KAQ and Argus, and none of those are available for you for this workshop. This is just background information. Now, if you have just one beam like L band and you're trying to do position switching, then you can do an on minus off command, on off. We also have off on if you want to do the off first. I tend to do that, but everybody's different. You could also just issue a track command. Again, these things in bold letters, big black bold letters, those are the actual GBT asteroid observing commands that you'll be using later today when you set up your observing scripts. So you can issue a track command and do an offset. If you're doing frequency switching, all you need to do are pulsar observations too. I should have had a slide here for Pulsar, a bullet for Pulsar. So I apologize for my Pulsar colleagues, which I need to update these slides for. There, you issue a track command. You just observe your source, track it. So as the Earth rotates, you keep the telescope pointing on the sky. And then for frequency switching, you can track the source and you're just flipping the LO back and forth. Pulsar observations, all they do is track the source and measure the total power data stream as it comes through. As I mentioned before, on continuum observations, for small sources, a daisy map is a good way to go. For mapping and large sources, then the question comes down to how big of a map do you need to make? Map size larger than your field of view. If the map is much bigger than the field of view of your instrument, like for example, the Argus instrument, the field of view is roughly 1.5 arc minutes. If you're mapping 30 arc minutes with a 1.5 arc minute field of view, you do an RA long map or a DEC lap map. Now, if your map is small, let's say you're observing, you want to map something that's like 1 arc minute, and your field of view is 1.5 arc minutes, then the question, there's like several factors that come into play there. You can still do the RA long mapping, but then you could lose a lot of time with the turnaround of the telescope, but you get nice uniform coverage if you do it that way. The DAISY map is useful if you're only interested in the central object. And in a lot of cases, people are, because they can sort of smooth the outer regions to get similar noise level. And they're just trying to measure, like doing photometry on a point source. As I mentioned before, you have this thing called a point map if you need to do a grid. And that's useful if you're doing a very deep spectrum and your beams are, packed in tightly. If you're trying to make a fully sampled map in your field of view, for example, like Argus, the beams are pretty far apart in comparison to the beam size. So You don't really gain that much by a point map because you'd have to make so many points to fill in the map that it's almost quicker just to do another type just on the fly mapping. And then we also have this thing you can do. The Mustang people use it for box scans. The idea there is you're basically bouncing around inside a box. It's sort of like a daisy, but it makes a more uniform coverage within a rectangular region. Okay.
Dave, here's a question
Yeah.
about pulsar observations. So do many pulsar observations require mapping?
Not that, no, they just look at that. Not that I know of. They do. Well, I'll hold that back up. If you're just looking at a pulsar, no, because they track that pulsar. If you're trying to search for new pulsars, then yes, you can map a region looking for pulsars on the sky. But typically, the targeted pulsar observations, no, they don't require mapping. Searching for pulsars, yeah, you can do mapping. And we do a lot of searching for pulsars, like when we're painting the telescope during the summer, the telescope just sits in the sky, rotates overhead. They just use that data to look for pulsars. That's a good question. I need to update my slides because more for pulsar work. So anyway, I'm going to jump into calibration. This is the GBT definition, or how we view the antenna temperature. I mentioned like doing the on minus off. So we do the on minus off divided by the off times the T-sys, and this scalar is off divided by, T-sys ratio. You derive that based on noise diodes, electronic noise electronic signals, where you know the temperature of effectively, or hot and cold lobes. For example, this is a high-tech data from back in '89. That goes back a while, of our educational telescope. And what they do there is like you're scanning across something. It's a transit telescope, so they're waiting for something to come across the sky, and you flicker to turn the noise on. The source goes over, and then afterwards you turn the source on. You know how bright this signal is. If you know how bright that signal is, you can estimate how bright your target source is. For the GBT, what we do is we flicker the noise diodes on. So if you take an off and on source, the data would look something like this, where this counts here, your blank skies. This is sort of like corresponds to your system temperature. You see this sawtooth thing here. That's the on minus off of the noise diode. And then you go on source, and the source goes on. So your data looks something like that. But the idea here, you know how bright the noise diodes are, this scale factor is, and from that, you can estimate how bright your sources are. A higher frequency, I mean, at 3 millimeters, we don't have noise diodes. We use hot and cold loads, but it's the same principle. You have a hot load or a cold load, you know those temperatures. So the difference between the hot and cold load, and then from that, you can derive the scaling between your counts you observe and your effective temperature of that you are measuring of the antenna temperature. All this is tied back. We tie it back at lower frequency, meaning under 50 gigahertz and below, we tie our calibration to the VLA. The VLA monitors a few of these standard calibrators, and these are the 4 that are relatively stable and over time, and they're used for absolute calibration. Now, if you get above 50 gigahertz, what I leverage, I use the Alma calibration database, and they do the same thing. They're observing a subset of sources, and I just use their source, their catalog for calibration. Now, we've had trouble the last year because Alma's been down due to COVID, where we kept on observing. So we've had to observe more planets, Mars, Jupiter, to try to do calibration with the Alma. I mean, at 3 millimeters in the last year, since Alma wasn't around. Because the Alma observations, the 3 millimeter calibration sources, most sources aren't right at 3 millimeters, and the ones that are highly variable. So you have to track their history very accurately. And Alma's looking at the same sources over and over again, like every week or every few days, and basically much more often than we are at 3 millimeters. So we just leverage their work. Okay, in terms of, I think this is basically my last slide, and I didn't even I wasn't even timing it that well, and we're going to finish about on time, which is good. This is just going to go over sort of what you need to do in terms of antenna optimization. At higher frequency, you need to point and focus every hour or even 30 minutes at Argus. Now we're going to only go up to K-band. So at K-band, you can get away with pointing and focusing every, couple hours at night. So since our projects we're getting 2-hour sessions tonight, even at high frequency night, we get away with only pointing once. But if we were doing Argus observations, even with the 2-hour session, you would be wanting to point and focus every 30-40 minutes. At lower frequency, you guys don't need to point or focus at all, but we do recommend that you go ahead and do a point, at least I do at lower frequency, just to show that the telescope is working. Not so much the fact that, you need an accurate pointing corrections, because you don't care about a 10 arc-second error when you have a very large beam. At higher frequency, and we're not going to do this for this session, so I guess we should talk about, we're not going to have an auto-OOF demonstration because we do not have a receiver on the telescope for which we will take an auto-OOF, except for Mustang, and we're not going to do the Mustang auto-OOF experiment. So we do not have, and we won't, so high frequency receiver we can use this K-band. Natalie will still give a presentation, Nick, tomorrow on high frequency corrections and get into doing the auto-OOF. A lot of times we'll do a demo showing the auto-OOF and the people will observe, but we will not be doing that for this workshop. So I think that's all I have in terms of questions. My slides, and let me get out here. Whoops, I'm not sure if I can see the chat. I'm going to stop my share. And then where's it? Okay. So 6 degrees, I'm going through. Okay, I'm just going to, Sonia put in a question with respect to antenna configuration. What is the advantage of putting a subreflector at an off axis instead of putting a receiver or horn antenna directly at the off axis? Okay, so we at lower frequency, the reason we have a Gregorian focus, and we have a turret and we could put a lot of different receivers or equipment there. We can rotate things in. In fact, you could argue, you could put a mirror down there and and reflect it back, and we have even more options. So the advantage of the subreflector is allowing us to be able to have lots of different receivers on the telescope at once to observe. At prime focus, we only have one receiver up at a time. So that would, and what we do for the prime focus feeds, we usually flip between 340 and 800 megahertz. One's up for a week or two, and the other one goes up for a week. So that's the advantage of having a subreflector, or in other telescopes, they do different optics. You can have a subreflector. A lot of times you have a subreflector that comes down into a room, and you can have a mirror or something, or another tertiary mirror or something that you can reflect the light to different equipment. Okay, does anybody else have questions? Might be too much information too quick. Matthew, you have your hand up. Feel free.
Yes. Can you tell us about any projects there at GBT that are using polar imagery?
We don't do it. We can make polarization measurements with the telescope. Typically, most of our most projects are done with. We measure both dual polarization as just intensity mapping. You can do it. There's some disadvantages, I think, with the off-axis design. It's harder to do like Zeeman measurements and Faraday rotation measurements because you have to measure what we call the polarization properties change with parallactic angle with our telescope, and it's an off-axis design. It's not quite symmetric, so you need to calibrate the polarization measurements pretty accurately, and that can take, unfortunately, as much time as the actual science observations themselves. And since we don't have enough people that do it, we haven't spent a lot of engineering time trying to quantify that with all the different frequencies. Have a hand up.
Can I interject real quick on that? I just did a search through our recent proposals, and the recent ones that did polarization were for FRB studies and also for polarization mapping of infrared dark clouds.
Okay.
So they're not too many, but that's a sample of some of the science areas.
I keep forgetting, yeah, for the fast radio burst and that kind of stuff, they do that. Wall, you had a question?
Yeah, thanks. Well, first of all, thanks, David, for the talk. Really informative. I just had a quick question about on-off measurements.
Mhm.
Why? I think you showed the plot where there's a noise diode flicking on and off.
Yeah.
On an off source, and then when you put the antenna on an on source, you also flick the noise diode on and off. And so I'm just wondering why do we need to use a noise diode in such observation rather than just using the on off of the source? If that makes sense.
Yeah, to be honest, we wouldn't have to flicker the noise diodes like we do as often, but you would still want to take an observation with the noise diode on and a noise observation with the noise diode off, basically, at least one. So some people actually do that because you want to set the temperature scale. So let's say you measure off, you just measure some counts, and then you measure an on, you measure some other counts. So you can subtract the two, but you have no idea the scalar calibration of what that means. So you measure some number. So what is that number? So the noise diode, and when you do it with the noise diode and on off with the noise diode, you know what that noise diode is. Let's say it's 10 Kelvin. So if you measure, so Vegas is measuring basically 10 million counts. So, and then you'll see it in the actual data, your on and offs will look exactly the same pretty much. And so your counts on source are maybe like, I don't know, 1,000, but your instrumental counts are something like 10 million. So it's just a way to do the scaling, to track the scaling of the temperature scale. Historically, radio receivers used to be relatively pretty noisy, so they'd flicker the noise diodes on because the gains were not, the electronic gains back in the day weren't very stable. So now we don't need to flicker the noise diodes on like we do. We just do it traditionally because that's how we've always done it. But you still need to have the noise diode. You turn them on or turn them off. So you could run a scan where you turn a noise diode on and off. You make a measurement of the noise diode. You know how bright the noise diode is across your band, and then you can just do your on minus off, and you can just have that one observation to scale everything. At the higher frequency, that's what we do. We put the vane in and measure your scale of your system, and then do your regular on minus off. I guess the thing I didn't point out is not only the noise diodes that you're measuring. Every time you balance or reconfigure the instrument, you're setting all these levels within the IF system. And although when we issue those commands to rebalance, ideally they're targeting the same sort of levels. They can vary roughly by 30%. So if you didn't have a noise dial on, you could be, and you weren't measuring it for a set of observations, you could be off by like 30% roughly. If you just measured a noise dial, let's just say one day at one time, and then you were observing another day, another time, you could be up to like 30% off in terms of your calibration scale. That's why we do it. You should do it at least for each set of observations, but it's a bit overkill for flickering because you don't really need to flicker it. And if you're really anal about it, it adds a little bit of noise and you're injecting a signal. So you're adding noise into your signal a little bit. There are people that actually turn them off, basically. But the default mode's just to leave them on. And that's how the software processes the data.
I see. And do you also rely on a flux density scale or flux density model of the source that you're doing an on-off measurement for?
Well, so what we do, you measure, think of it, I'm back. You're using the noise dials and you're tying a temperature scale. And then you have this noise diode signal. And then what we do is then go measure something that we know, like a 3C 286. We know its absolute brightness. So then that ties it to the absolute calibration scale. So you can think of the noise diode doing relative calibration throughout your experiment. And then you do an absolute measurement by looking at it, like 3C 286 or something of known brightness.
I see. Okay, makes sense.
Because the noise diodes themselves are stable on the timescales of 6 months or maybe a year, but we don't change them that much. So they're the calibration table. So what we do is they can drift over time. So ideally, you'd want to observe something with the noise diodes of something you know, and then that gets the calibration as accurately as we can get it, which is you can do better than 10. If you're careful, you can do 5 to 10% flux calibration absolute with the telescope. If you're sloppy and just use all the defaults, you can be 30 to 50% off.
I see. Yeah, thanks, Dave.
Yeah. Okay. So we had another question coming in from Sonia. I'm just curious to know, what is the regular checkups that GBT has to go through in order to maintain its health, or before allocating a schedule with the GBT? Well, the GBT, I'm trying to think the context of this question here. We're constantly observing. So when we put a new receiver up, we check out that receiver. When something breaks, the operators let the scheduler know that something's broken, so they don't schedule it. So typically, every time a receiver goes up, it gets checked out. If something obviously happens, we know it's broken and it won't get scheduled. Occasionally, something subtle happens at some point, and the operators don't catch it, or previous observer doesn't catch it. And you can take data with a broken instrument in a way, and sometimes the observers are the first people to notice, oops, something's going on, that's wrong. So that's why we like to train our users to have some expertise with the telescope, so they can actually provide feedback too when they see something. So if you see something early, you say, hey, this seems to be broken, or there's something funny going on, then we have the operators will call on a scientist or an engineer, or a lot of times it can be software related, an expert, and then they try to fix your problem. I'm not sure if that answered your question or not. I'm not sure if that was a context of which you're asking, or if you're looking at something else.
So Dave, you said that when a receiver goes up, it's checked out. What does that mean?
Thank you, Will. We use this jargon all the time. That's why I like informal things, because we get caught in our jargon. When we basically take some test observations to make sure that it's performing as expected and all that it's working properly before we hand it off to the users. Sometimes things are not checked out as well as they should be before we hand things off to observers, but that's what I meant by a checkout.
And usually that's like a 3C 286 or as a bright quasar that we check to see if its intensity scale is what we expect. Yep.
Yeah, the noise scale, and then you can point, and you're making sure the signal's coming down all the paths properly. And because occasionally, it hasn't happened for years, that they can put the receiver, if you have a multi-feed receiver, they can put it in backwards or rotate it around or connect it up the wrong way. So you say, hey, that should be beam 1, but hold it. No, anyway, to make sure it was connected properly. Those issues were way back in the early 2000s when everything was new. The engineers have their own checklists they go through to minimize those wiring connections. But earlier on, if you're taking receivers, it's not a simple thing to take. We do it all the time, but it's not simple. If you go up in the receiver room, you see all those cables, they have to get unconnected and taken out and reconnected to something else. There's a lot of work involved there, and there are some sources of error that could crop in, but they're very careful. Okay. So thank you, Sonia, for following up. She said that was a question pointed by Will. Okay. Are we any other questions before we move on? We're So is it Amber or up next, or who's up next? Will?